We are still in Unit 7. This is our second section, and today we're going to start volumes. Today we are going to take a look at volumes of solids with given cross sections. So I'd like to begin by developing what we're going to be doing, and to do that we're going to take a look at a shape here. I'm going to graph a region. Okay, I'm going to graph a region. Let's say that one side of the region is the y-axis, and one side is this part of a curve f of x, and then the other side is this part of a curve which is g of x. Okay, so let's say that those are our region is right here. Okay, so let's say that this is going from, you know what, let's not make this the y-axis, let's make this y-axis over here. So this is just x is equal to a, this is x is equal to b. Okay, perfect. All right, now listen carefully, because I'm going to describe a solid. Right now you don't see a solid, do you? I hope not. This is just a two-dimensional region, right? The solid that I'm going to describe has this as its base. So this region R is the base of a solid. So think of the solid coming up out of my page, out of my paper. Okay? All right? Now this solid, I'm going to tell you what the cross-section of the solid is. Okay? This solid has cross-sections. If we take a cross-section perpendicular to the y-axis, so like this, if we take a knife and just go cut it right into a slice, right like that, the cross-section, we're going to start off saying the cross-section would be a square. We're going to have different shapes, but this time it'll be a square. So let's think about that. Each cross-section is a square. So there's a solid. This is the base of the solid. Each cross-section perpendicular to the x-axis is a square. So I need you to try to visualize this. Okay? So if I took the slice like right here, think about that. If I took the slice right there, there would be a square coming up out of the paper. So I'm going to try to draw that, but I'm going to tell you it's not easy to draw this. So the square is coming up out of the paper. Can you kind of see it coming up out of the paper? So that would be one cross section. If I took the cross section right here, it would be a tinier square, right? But it's still coming up out of the paper. If I took the cross section here, it would be a bit of a larger square coming out, still coming up out of the paper, right? And the largest square would be if I took the cross section right here, right at x is equal to a in this case. But if I took it here, you can see this cross section would be quite a bit bigger than that cross section. So can you kind of visualize what's happening here? Can you visualize the solid? And then this solid would be solid. It's a solid. All right? Our goal is to find the volume of that solid. I'm going to draw this last one over here. Okay? So our goal is to find the volume of that solid figure. Okay? So let's think about, just like we did with our areas, I want to take one of these and examine one of these. So I'm going to take this piece right here, and do you agree that it has area, doesn't it? It has area. It has area. In fact, we know a formula for the area of a square, don't we? Okay. So we can find the area of that. Now we're going, since we want volume, I need to give this slice through my solid, I need to give it a little bit of a width. So I need to give it a little bit of a width. Let's get a different color. A little bit of a width here. A thin width, but a little width. Okay. Do you agree that that little width is in the x direction? So that would be a little delta x. That would be a delta x width, wouldn't it? Do you see that? It's a little delta x width. Now let's think about volume. What would the volume of that piece right there? It's a prism, isn't it? Isn't that a prism? Yeah. If I give it a little width, it's a prism. So the volume of that prism would be length times width. In this case, length times width are the same, right? Times delta x, correct? So it would be the area of that slice, whatever it is. It would be the area of that slice, and that would be in terms of x, right? Because this would be, if we were finding this length right here, the length there, we did this yesterday, the length there would be f minus g, right? Top curve minus bottom curve, f minus g. So that has x's in it. So the volume would be the area of that cross-section times the height of that little prism, which is delta x, right? That's the volume of one slice. That's the volume of one slice. What are we going to do with all of those slices? Well, with all the areas, we're going to add up all the areas from the first one, whoops, I equals, we're just counting, I equals the first one to the nth one, if we have n slices. And then what are we going to do with n? We're going to let n go to infinity, and we get the integral from x equals a to x equals b of the area of our slice times dx, the height of our slice. Okay? This is our formula for volume. Okay? This is our most basic formula for volume. This works no matter, this time they were squares. What if they were triangles? What if they were semicircles? What if they were circles? What if they were whatever? This works no matter what the cross-section is. We just find the area of the cross-section and multiply it by dx, delta x. Okay? Or if our slices were perpendicular to the y-axis, then we would need a dy, right? Okay, so because our volume is so much based on area, we need to review some of the areas of different figures that you might come across. So let's start with square. With a square, we know the area of a square is just side squared, right? I'm going to let S be a side. Okay? In our case, S would be f of x minus g of x in this example, right? So the area would be f of x minus g of x squared for a square. What if we had another one that's common is a circle. You know what? I'm going to save a circle. Let's do some of the easier ones first. What about an equilateral triangle? An equilateral triangle. I would like my area to be in terms of the side, right? So think about an equilateral triangle. Think about, I'm asking you to think back to, I don't know if you did, you may have done this in pre-cal, mostly in geometry though. I think you did do this in pre-cal. Anyway, if this if this is our side, I'm going to call that x. If that's x, okay, then what is the area in terms of x? What's the area in terms of x? Well, the only thing we know for area for a triangle, our most basic area of a triangle, is 1/2 base times height. We want to get x involved. Well, I know the base is x. What's the height? There is the height. What is it? In an equilateral triangle, remember, in an equilateral triangle, if this piece is 1, then the hypotenuse is 2, and the ratio of the, in a 30, 60, 90, this will be a 30, 60, 90 triangle, right? The ratio is 1 to square root of 3, right? It's 1 to square root of 3. So if this is x, then this half of this would be x over 2. So this side would have to be x, and the height would have to be square root of 3 over 2x. That would be the ratio, right? So the area would be 1/2 the base times the height. So it would be square root of 3 over 4x squared. So the area of an equilateral triangle in terms of its side is square root of 3 over 4 side squared. I'm going to put all these in terms of side because that's going to be easy for us to find. Okay? All right. What about an isosceles right triangle? Isosceles right triangle. In an isosceles right triangle, we can actually have two versions. We can have one where the leg is on the base, so that is S. And then we can have one where the hypotenuse is on the base, so that is S. So do you see the two different kinds? In the kind where the leg is on the base, in the region where the leg is S, in this one, the area will just be 1/2 base times height, so just 1/2 S squared. So leg as base, leg as a side, let's put it that way, the leg as a side, so leg on the base, that would be 1/2 S squared. And then the other version would be the isosceles right triangle with the hypotenuse as the side, as the base side. So for that one, what would that be? What is the ratio what's the ratio of the sides in an isosceles right triangle? So the ratio is 1 square root of 2, right? So if this is S, then what would this be? That would be S divided by square root of 2, right? Makes sense? So the area would be 1/2 base times height, where the base and the height are both S over 2. S over square root of 2. So this becomes 1/4 S squared. So with the hypotenuse as the base, the area is half of what it was before with a leg on the base. So this triangle will be much smaller. Okay? All right? What about a semicircle? What about a semicircle with the diameter as the base? Okay, let's come off to the side. Semicircle. Okay, so this is my side. Okay, well, I know that the area will be 1/2 pi r squared, right? Where r is, what is r? R here is half of S, right? So this would be 1/2 pi times 1/4 s squared. So that is pi over 8 s squared. So in terms of the side, for a semicircle, the area will be pi over 8 s squared. Okay? And we'll take a look at circles tomorrow, in tomorrow's lesson. Find out what's going on with that. All right? So, on your notes sheet, at the top of the page, let me grab my note sheet. At the top of the page here, in this box I have these. Add to it semicircle though, into the circle. The area will be pi over 8 s squared. These are all things that you should know without having, I don't want you to have to do this every time you need an area, okay? So it will be convenient if you just know these formulas for area without having to develop them each time, okay? By the way, I have some pictures of some other, so this is one where what we just did. There's the base, and here are the squares coming up out of the page, right? This is what the solid would look like in that kind of a scenario, okay? Because they'd all be lined up together. Here is one. Here's a picture of one that they made with equilateral triangles. Okay, you see the flat base and the equilateral triangles, where a side is on the base of the triangle. Here's another one that looks like equilateral triangles to me. Okay? And then in this one they made it, and it has, this one is made with semicircles. This one looks like squares. This one looks like isosceles right triangles, because I see that straight edge over here. And this one looks like rectangles. If you have rectangles, then just remember your area. Remember, it needs to be the area. So you're finding the area of that rectangle. One side will have x's in it, and then usually you're given the height as a number or something else. Okay, let's take a look at some examples. And usually what I do is I'll come down and I'll do the second example first. But I think I'm just going to do the first example first for you guys. Okay, so key here, when you see, find the volume of the solid whose base is bounded by a circle with indicated cross sections. When they start talking about cross sections, hopefully it'll be perpendicular to the x-axis, so that you can just do that means perpendicular to the x-axis means each slice is going to have a little delta x. So those will all be dx's. All right. So if it's going to be delta x, then we need to take our equation and solve it for y, because we want x's, right? So first of all, let's take this equation and solve it for y. So if we solve this for y, we're going to subtract x squared from both sides, and then square root both sides, and we're going to get a plus or minus, right? So we're going to end up with two equations, the positive square root of 25 minus x squared and the negative square root of 25 minus x squared. And those will be the two halves of a circle, right? The top half will be the positive square root. The bottom half will be the negative square root, right? Okay, so that's the base of the solid, okay? In part A, each cross-section is a square. So I'm going to start by drawing my little slice, my little perpendicular to the x-axis slice. And I need to find that side length. So what is that side length? Well, the side length is the top minus the bottom, right? The positive square root minus the negative square root. So the side length will be 25 minus x squared minus negative square root 25 minus x squared, which of course is 2 times the square root of 25 minus x squared. So that's our side length. We're going to need that each time. Okay? It's just top minus bottom. That's all it is, which is what we've been doing since yesterday, right? Okay, so for squares, I know that my area is side squared, right? And there's my side. So my volume will be the integral of just the area dx, right? What are my boundaries on my integral? What is my leftmost x and my rightmost x? If we're doing a delta x, that's where we go to. So what's my rightmost x and my leftmost x? Well, this was a circle of radius 5, so this has to be going from -5 to 5. -5 to 5. Okay? And so we just have the area, the side squared, so this will be 2 times the square root of 25 minus x squared all squared dx. Okay? Let's see what that gets us. We're going to just use our calculator for these. Again, we could do this by hand, but we're just using our calculator to save some time. This is from yesterday. Okay. So math 9, -5 to 5 of, okay, parentheses, 2 square root 25 minus x squared, close parentheses, square the whole thing, dx. Be careful typing that in. Okay, I think I'm going to change. We could write this as a decimal. I think I'm going to change it to a fraction, and I'm doing that for a reason because you'll see in this subsequent problem. Okay? All right. Now, in this particular base, we have symmetry, don't we? Do you agree? We have symmetry. So an equivalent, we could have just done from 0 to 5 here and doubled it, right? That would have given us the same thing. Could have done that. Okay? So in some of these, we do have some symmetry, so you can play around with the integral a little bit. It doesn't really matter. I mean, since we're putting it into our calculator anyway, it doesn't matter. But if I was doing this by hand, I might want to deal with a 0 as a boundary instead of a -5 as a boundary. Okay? All right. Next up, what if our cross sections now are equilateral triangles? So what is the area of an equilateral triangle in terms of its side? That's our square root of 3 over 4 side squared. So the volume will be the integral from leftmost x to rightmost x of the area. S is our 2 times this, and then we square s. We only square s dx. Look at how these two compare, you guys. Do you agree that they're exactly the same except for the square root of 3 over 4, which we could take out, right? We could take that square root of 3 over 4 out, and we would just be multiplying this answer by square root of 3 over 4. So that's what I'm going to do there. That would be 2,000 over 3 times square root of 3 over 4. Yeah? Which would be 500 square root of 3 over 3. Okay? Next up, semicircles. So now each cross section is a semicircle. So this has to be the diameter of that semicircle. So the area of the semicircle in terms of side for the diameter will be, again, pi over 8 side squared. So the volume will be the integral, -5 to 5 again, pi over 8 side squared, which is the same thing as this we had at the beginning, except for this factor of pi over 8, which we can take out. So this will be just 2,000 over 3 times pi over 8, right? Which is, let's see, what's 2,000 divided by 8, you guys? 250. Okay, so 250 pi divided by 3, if you wanted to reduce, or if we needed to reduce to get a multiple choice answer. Okay, next up, isosceles right triangle with a leg on the base. Leg on the base, remember that that area is the regular 1/2 s squared. That's the regular. Hypotenuse on the base shrinks it and it makes it a 1/4. Okay? Alright, so volume will be integral -5 to 5 of 1/2 s squared. The 1/2 can come out, and so we're going to have half of what we got at the very beginning. So this would be 1,000 over 3. Okay, one more thing. Since you named s as the square root, the 2 square root of 25 minus x squared, since you named that there, we could have written s squared here. S squared, s squared, s squared. We could have written that instead of rewriting the 2 square root of 25 minus x squared each time. Okay? Example 2. Find the volume of the solid whose base is bounded. This would be more like what it's like on your, what you will see. So we have the base is bounded by, so here comes the region. Y is equal to x minus 4, that's just a line, slope 1. Y is equal to 4 minus x, that's just a line, slope -1. X equals 0 is the y-axis. And then we have indicated cross sections taken perpendicular to the x-axis again. X-axis means delta x dx, right? So, let's sketch out what's going on here. Y equals x minus 4 is a line with slope +1 starting down here at -4. So this will be like that, right? Y equals 4 minus x is a line starting up at 4 with slope -1. So something like that. Okay? And then the y-axis is also a boundary. So where's your region? Well, we see the region, it's right here. Begin by drawing a little representative rectangle where you need it. And that will help you visualize, okay? That will help you visualize. So we need to get this side length. What is that side length? What is S here? Well, S will be the top minus the bottom, right? Top minus bottom. The top one was this one. So that will be 4 minus x minus the bottom one will be the x minus 4. I'm going to simplify this because we're going to be writing it several times. So this will be 4 minus x plus 4, right? So that is 8 minus 2x. That's easier to write than that other thing. Okay. Cross sections are squares. So we need the area, and that will just be, for squares, the area will be s squared, right? So in our volume, the volume will be the integral of the area dx, right? What's our leftmost x value? Well, the leftmost x value is 0 because we're on the y-axis there, right? What's our rightmost x value? 4. 0 to 4. And it'll just be s squared. And yes, it's okay just to write s squared. Just make sure it doesn't look like a 5 squared, because that would not be correct. And what do we get here? Let's use our calculator for this one. Integral math 9, 0 to 4, parentheses, 8 minus 2x, close parentheses, squared, dx. And then again, I'm going to change that to a fraction, 256 over 3. Okay. What if our cross sections are equilateral triangles? Well, the area of an equilateral triangle is square root of 3 over 4 s squared, right? So the volume will be the integral 0 to 4 of square root of 3 over 4 s squared dx. I need to see your integral each time. But now I know that this is exactly the same as what we just did, except for that square root of 3 over 4. So I need to multiply square root of 3 over 4 times 256 over 3. 4 goes into 256 64 times. So this will be 64 square root of 3 over 3. Okay. What if each cross section is a semicircle? So then the area will be pi over 8 s squared. So our volume will be integral 0 to 4 pi over 8 s squared dx, because we have to give it a little thickness. Okay? So again, this will be pi over 8 times what we got from our first integral. Yeah? And 8 goes into 256, 3, carry the 1, 2, 32 pi over 3 will be that reduction. Isosceles right triangles. This time the cross sections are isosceles right triangles, hypotenuse on the base. Hypotenuse on the base is that little smaller one, right? So the area is 1/4 s squared. Okay? Volume will be integral 0 to 4 1/4 s squared dx. So our answer will be 1/4 of our very first integral here, which is just 64/3. Not bad. I don't think it's bad. So remember, you guys, up at the very top of this page, I want you to put this. Volume is equal to the integral from a to b of whatever your area function is, dx. Your area will have x's in it. If your area has y's in it, then we didn't do an example like this, but you can totally have y's here when you have a dy. That would be cross sections perpendicular to the y-axis. Okay? All right. That's it. Time for you to go practice.